So we just tested in our last class on chapters 1 and 2. So we've now basically finished kind of the preliminaries and introducing a few new concepts that are foundational to our work going forward. We have spent 7 weeks on that in order to get to this point. We got about 29 weeks, it's actually more weeks, but 29 weeks worth of days left this year, and we're going to be using that for chapters 3 and 4, where we really get into a lot of the nitty-gritty about calculus and finding derivatives. At the college level, because this is a college and the high school class, so I want you to have some perspective. If we were doing this at the college, you have one term. A quarter is 10 weeks long. So we'd be just about done with chapter 4, which means that chapters 1 and 2 would have been done in the course of maybe 2 or 3 weeks, what we just did in 7. So that's just kind of a little bit of an idea about, we have a luxury in here where we can take a little bit more time. Yes, this is a college level class in terms of its content, but not in terms of its speed at which you have to learn it. So just be aware that as you go into college math and are taking math at the college level, you're going to feel like they're going really fast at first. And that's just part of the deal, and there's going to be an adjustment period there, but I kind of want to forewarn you about it so you're prepared for it. All right, we're getting into some new stuff today. And to start with, I just want you to make up 3 polynomial functions, any polynomials you want. I'll write them up here, and we'll find the derivative of those. All right, so we just got these 3 made-up polynomial equations from you all. We now need to find the derivative. Okay? So, how long would it take you to do the derivative of that first one? Yeah, it could take a little while. Although, I can actually just look at it and tell you that the derivative is 3x squared minus 2x. You made up the second one for me. Okay, the second one, the derivative is 2x plus 4. The third one, you made up that one for me as well. That derivative is 2x minus 15. I want to keep going with these. Give me some more. All right, so we got 3 more random ones. The derivative of this first one, x squared minus 25, is 2x. The second one, negative x to the 7th plus 9, our derivative is negative 7x to the 6th. And for that last one, we end up with negative 2,340 x to the power of 4. And that's it. Aren't you glad you aren't having to do that out by hand by difference quotient, right? Let's see if you can start figuring out how I'm doing this. Give me a few more, and let's see if we can start narrowing down a method here. Through a number of examples, you might be able to start noticing some patterns. All right, so 3 brand new ones all made up. You should be working on getting to know them yourself. See if you can find these derivatives yourself before I put them up here. All right, so that first one, my derivative is 2x. The second one, 4,000x to the 5th, that would be 80,000 x to the 4th. And then the last one would be 7x to the 6th minus 6x to the 5th. Are you figuring it out yet? And an error was brought to my attention. There was an error in this one. I did a little bit of mental math wrong. That should have been 20,000 x to the 4th. My apologies for the error in the mental math there. More, please. All right, so then, for this set of derivatives, then, you would have negative, oops, I forgot something. And again, be making sure that you are actually looking at these first and seeing, can you figure out what that derivative is? All right, next one. And our last one. By now, you should be noticing a pattern here. You should be able to figure it out pretty well. Let's do one last set. Can you go ahead now and test any last little theories like, okay, well, I think it's this, but I'm not sure. Let's test any of those. All right, so our last ones here to check out. The first one, our derivative is 2. Next one, 120 x squared plus 40x. And our last one, negative 0.9 x squared plus 1. Hopefully by now you've kind of seen the pattern. You've started to see how these work and how you could find these derivatives so much faster than having to use the limit of the difference quotient, and to test and see whether that is indeed the case. Here are 6 that I made up for you. Please find the derivative of each of these functions. And to check your answers here, let's make sure you got those down right. For the first one, f of x. 18. And actually, yeah, exactly. We get 18x. And I'll actually go around and I'll go get answers from you all for all the rest of them as well. All right, so these are our answers as we look through. And a lot of these we've seen before, but nobody decided to try to challenge me with a negative exponent in those other ones. So if we take a look and see what happened here, on all of these, like looking at this one as an example at G, notice my exponent went down by 1. Well, the same thing happens with this negative 3 as well. What's negative 3 minus 1?
Negative 4.
Negative 4. So it actually ends up still following the exact same rule. We are still subtracting 1 from it. What you have just learned to use by going through these examples is something called the power rule. The power rule is kind of the very first and foremost of all the different derivative rules that you're going to be learning here in the near future. This is what Chapter 3 is all about, is seeing how we can find derivatives without having to go and deal with the limit of the difference quotient. And so we're going to be finding all these other techniques, ways that actually should be making it a lot easier than having to go and use that. Now, because we're going to be doing lots of notes on these derivative rules, you'll want to start a sheet. You might end up even using 2 pages by the time we're all done with it. Title this new page in your notes Derivative Rules and make it a page unto itself. You're going to want to be able to go back to this sheet and find your derivative rules anytime you're feeling stumped. So don't mix other stuff into it or anything like that. And then the first rule that gets added onto your derivative rules notes is the power rule up here. So please add this now into your derivative rules notes. Now you'll notice here that the power rule by itself doesn't actually let us find all the derivatives that we've already seen how to find. Because you'll notice that this only tells us when it's just x to the power of n. It doesn't tell us about what happens with any number out front of it. But we did see that in action. We saw that if there's a number out front of it, like let's say I called that m, that would mean that out front I would actually be doing m times n, that sort of a thing. Well, that is also a derivative rule. And so, add this into your derivative rules, please. All right, so what this rule is telling us here, notice it's saying if f of x equals c times g of x, and that is just multiplication going on there. So what it's saying is that f is just a constant being multiplied by some other function. So this would be like our 3x squared sort of thing, where 3 is the value of c and g is x squared. So notice what that's telling us is that when I find the derivative is just going to be multiplied by the exact same constant. So that constant that's being multiplied by it doesn't change like how we have to do the derivative or anything. So we saw that already when we were using power rule in those early examples. All right, now here is the kind of example we were just looking at. You should be able to find the derivative of this one quick and easy, right? So go ahead and please find the derivative of this function, and then we're going to riff off of this for another one and see what we can and can't do. All right, so when you go and find the derivative of this one, you should have gotten f prime of x equals 6x squared minus 6. Okay, no problem, right? Now please find the derivative of this function. All right, now looking at this one way that you might have gone about doing it is you might have started by just trying to simplify this a little bit. Like, let's get rid of the parentheses. So if I do that, I do the 2 times 6, which is 12, and x cubed times x is x to the 4th. And then, okay, I'm looking at that. That looks like the stuff I was just finding the derivative of. So now I can find my derivative to be 48x cubed. Okay, great. But I said that was one way you might have done it. There's another way that you might have done it as well. You might have also gone straight to g prime of x equals 6x squared times 6. But if I multiply those together and simplify that, that would give me 36x squared. That's not the same, is it? So notice that when I just find the derivative of each of those two parts and then multiply them, I got something different than multiplying them first. So which one is right? Well, the correct way to do it is actually the first way that we did it, is actually to multiply it out. It turns out that when you multiply these together, you cannot simply multiply two derivatives together and have that equal the same thing as the derivative of the original product. So while we saw that that worked with adding and subtracting on that last problem, it does not work with multiplication. Now later on we'll be actually adding a rule to your derivative rules page that tells us how to do it with multiplication, but for now, all we can add on there is the derivative of a sum or difference, which does not extend to products or quotients. So, derivative of sum or difference is the derivative of the sum of each term. All right, now as you're copying this down, you'll notice something new showing up in our rule. Well, how would I write f plus g and saying I'm going to find the derivative of that? Like, would I write f of x plus g of x? Like, can we do prime like that? That looks kind of awkward with it. So what we end up seeing is another way that we can represent the derivative notation, and this is something we're going to go into even more detail on tomorrow. But this d over dx that you see cropping up, that's another way that we can represent derivative. And so what you're seeing here is that first one is saying the derivative of the sum. So if I take the whole equation and am adding them first, and I want to find the derivative of that, then I am allowed to do the derivative of the first term plus the derivative of the second term. That's what that's really meaning. So d over dx, that still just means derivative. There's actually lots of ways that we can write that meaning, which again, we'll talk more about that detail tomorrow. Right now, let's see if you caught one other little detail here. Please find the derivative of each of these two functions. All right, so with these two, you may have caught what the derivative of these were when we did it earlier, but it might have skipped by a little bit unnoticed because sometimes things just disappeared. We need to see what was actually happening when they did. So let's do a little bit of an example here, a little bit of a visualization. Let's say I was graphing this. And so if I was going to graph f of x equals 8, that's like y equals 8, right? The equation y equals 8 is a horizontal line passing through 8. Now remember what derivative means. Derivative means the slope of my tangent line. Well, this is a line, so it's just going to be the slope of the whole thing. What is the slope of that line? Well, notice there's 0 rise and there's whatever run you feel like. 0 over anything? Yes, we can do that. F prime of x here equals 0. And so then g prime of x, well, it equals -3, but it still would be a horizontal line if we graphed it. That would still be 0, which in some of our earlier polynomial examples that we were looking at, we would have a number in there, and it would just disappear when we took the derivative. This is the reason why, because it was becoming 0, and we didn't actually have to write plus 0 in there, so it just went away. Well, this then gives us one last rule that we can put into our derivative rules for today, the derivative of a constant. Now, if I were looking at a really quick example again, another separate example to do here, f of x equals 8x cubed, and I'm finding the derivative. The one mistake that sometimes people start getting lured into because of this particular rule up here is they'll say, oh, well, the derivative of 8 is 0. And the derivative, and 0 times anything is 0, so then that whole thing would become 0. They start trying to get caught up into that. But remember, this is only if the entire function is a constant. In this case, this is actually going back to the constant multiple rule, which we learned earlier, which is saying that I'd be doing 8 times the derivative of x cubed, which is 3x squared, which is why we still get the 24x squared out of that. So don't be lured into thinking that the constant here turns everything into 0. That's a little bit of a trap that sometimes people can fall into. All right, now one last little note, going back to the very first thing that we talked about, the first thing that you put into your derivative rules was the power rule. And there was this little caveat in there where we said that n cannot equal 0. So, why did we have to say n cannot equal 0? Yeah, because anything to the power of 0 is 1. So if I gave you the derivative of that, that's actually saying find the derivative of 1, which is a constant. And the derivative of a constant is 0. And if we aren't careful about that, we might misapply it, because if you try to turn that into like x to the -1, you're going to be running into some trouble along there. So just be aware of that as you're going through your derivatives.